Not lunchtime yet. So this is going to be 1.3 B. This is going to be the squeeze theorem. Theorem and trig limits. The squeeze theorem and trigonometric limits. Now, some people will wonder, are these really going to be on the AP test? Last year, there was a question about the squeeze theorem on the AP test. And in years past, it has existed. So you need to know what it is. You need to know how to use it. And you need to know what it looks like. So let's talk about the squeeze theorem, and then I'll show you a couple of trig limits that you need to just memorize, really. So the squeeze theorem, not squeeze with an S, squeeze with a Z. Squeeze theorem says the following things. If, let me see how to say this. So it involves some functions. So let's say if h of x, some function, is less than or equal to f of x, and f of x is less than or equal to g of x, for all x in an open interval let's just say for all x and containing C, then if the limit as x approaches some value of h of h of x equals some number L, we'll call it L, and the limit as x approaches C of g of x also equals L, then by the squeeze theorem, the limit as x approaches C of f of x equals L. This is your squeeze theorem. If there are three functions, you have three separate functions. There's h, g, and f. So this squeeze theorem is simple when you get it. It makes total sense when you get it. But wrapping your head around it is going to take a second. So let me explain what all this stuff means. If there's these three functions, h and g, and f is between them. F is between them, meaning all the parts of h is always smaller than f. Everywhere in the graph, h is smaller than f throughout the whole function from beginning to end. And g is always bigger than f. G is always larger than f from all the sections. Okay? And if we do a limit of h and if we do a limit of g to the same place, and they both equal the same number, h and g are both connecting together down to the same spot, right? And then they separate, same spot. That means that f has to be in that same spot. Let me draw you a picture here. Let me draw you a picture, for example. So if I have this function, these functions here, let's call, here's some function g. Okay? And here is some other function h. Okay? Here in the middle is going to be here in the middle is going to be function f. Okay? And so right here, this is where I'm going to call C, some location of the graph. And here, this is going to be L, whatever value of the spot the graph is located at, the function is located at. So what the squeeze theorem, we see the squeeze theorem, what it's saying is that if you have G is like higher than F everywhere. G is always bigger than F in the entire equation. G is always above the function F. H everywhere is always below the function F. But at this spot, they come together, right? G and H come together, and they kind of squeeze F down to a certain point. We know that at this particular location, the limits of H and G are the same. They both equal L. Right? That's what this part says here. If, oh God, not that one. If the limit of H is L, and so here's H coming up, and there's H is L, and it goes back down. At this spot C, right, as x approaches C, the limit, right here C, the limit is approaching this value L. And G is also coming down and getting to C at the same spot, and C is, here's L at C. G comes down, H comes up, and they both touch the same spot. We know that F is always between. Everywhere F is between G and H. That's what this says up here. F is always between H and G. For all x values in some interval, but basically all x values. H is always lower, G is always higher, and F has to be between. It only works in this particular situation. If you know that G is always bigger and H is always smaller, and F is between them, and if you know that the limits of H and G are both some particular value, that means that the limit of F has to be that particular value as well. Let me show you a situation where it does not work. So let's say here's G, and here and here's H, okay, and here is F, right? And right here, this is where C is. Would this qualify for the squeeze theorem? I got a problem here. I got a problem. Right? Here, H goes, it is below, right? Here's H is below here, but then H changes to be above here. Let me do this in red. Here, right, H changes to be above the graph. And here G is still above, but H switches, right? So H was down here below, but it's higher here. So this is not allowed. This part right here. Let me try to draw this a little better. H is above F, so does not qualify for the squeeze theorem. Or we could have a simpler example. Here's G, here's H, and this will be I'm gonna do F like this. F like this. Oh God, stop it. F will be like this. Right here, yeah. So here's, let me do these in colors. Here's H. Here's G. So you see what happens. Again, this is not, does not qualify, because H and G are not this, like, they don't stay below, right? G goes from below to above, H goes from above to below. They're not consistent, they're not constant, right? So we see that from the graph here that these are not allowed. So how do we use the squeeze theorem? How do we use, like, where does this help us? Using squeeze theorem. So if we had two functions, let's say c was equal to 0, and we had a function like this. We had 4 minus x squared, and then some function f, and then we had less than or equal to 4 plus x squared. And I said to you, find the limit as x approaches 0 of f of x. Let's say I didn't even have this information. So I didn't even have this. I have two functions. I'm stating for you that this function 4 minus x squared and this function 4 plus x squared is always bigger and always smaller than some equation which I do not know. I do not know what f is. But I know that it's always between these two equations. So what you do is do the limit of I don't know what you call them, of this one. You do the limit of this one, and you do the limit of this one, of the edge functions. So I'm going to do the limit as x approaches 0 of 4 minus x squared, which is less than the limit as x approaches 0 of f of x, which is less than or equal to the limit, limit as x approaches 0 of 4 plus x squared. Minus x squared. So I'm doing the limits of the ones I know. Test the outer ones. Test the outers. If they're the same, you know the middle one has to be the same too. Maybe we say instead of edge, we say outside. Do the limits of the outside functions. And if they're the same, then we know we have the squeeze theorem. So if I plug this limit in, I mean, I can just substitute 0 for x. I'm going to get 4 minus 0 squared, 4 plus 0 squared, and that's going to be 4. Right, so I've like applied the limit to all three of these. I've given the limit to all three. Limit as x approaches 0 of f of x. As x approaches 0 of f of x. And so now I see that the two outer limits are equal to 4. And so I would say by the squeeze theorem, the limit of as x approaches 0 of f of x equals 4. That would be the way we would use it. Test the outer ones. See if it's the same. Questions about this theorem? So think of it like a sandwich. You've got a top function, you've got a bottom function. You find the limits of those functions. If the top sandwich, if the top piece of bread is equal to the bottom piece of bread, you made a sandwich. And so you know what the middle is. The middle has to be the same. As long as your top piece of bread is always bigger, it's always on the top, and as long as your bottom piece of bread is always on the bottom. If it doesn't look like a sandwich, right? If it looks like some kind of crazy crossways sandwich, or like some wiggly, like the breads intersecting each other in weird ways, it's not a good sandwich. Not going to make a good sandwich. Not going to use the squeeze theorem, right? As long as we know that everything is lower or higher, then we know we have a tasty sandwich, and we can use the squeeze theorem. If the top piece of bread equals the bottom piece of bread, we can have a delicious sandwich. All right. So again, the concept is pretty clear. It's pretty easy to understand once you get it. But wrapping your head around it, getting the idea, understanding under what circumstances this works is going to be the key. And that's true for a lot of these kinds of things in AP Calc. If you know the circumstances, if you see all this complicated looking explanation, but when you see the concept, when you can understand, oh, we're talking about just an upper function and a lower function, and then they meet somewhere. And that tells us, the squeeze theorem tells us we can combine these together. Okay. All right. Let's finish up with trig limits. Now, there are only two trig limits that you need to know. And these you just need to memorize. The limit as x approaches 0 of sine x over x equals 1. That is one of them. The other is that the limit as x approaches 0 of 1 minus cosine x over x equals 0. These are the two key trig limits that you need to know. And really, if you want the general form of the sine of, if you do this limit, sometimes it doesn't look exactly the same. They put numbers in them. So for example, if you do the limit as x approaches 0 of sine of, let's say, m x, like some number in front of x, over some number n times x. If you put numbers in front of those, whatever number you put above the, in front of the x in the sine, whatever number you put in front of the x on the bottom, your answer is going to be m over n. Basically, the sine ones, they all cancel out. Sine of x over x cancels out, and whatever numbers you have become your limit. For example, if you have the limit as x approaches 0 of the sine of 2x over 5x, you know this is going to be 2 over 5. Done. And it's just something you're going to have to remember and memorize. The cosine 1 is just 0 all the time, so it doesn't matter. Okay. And that's it for trig limits. These are the only ones you need to know. Everything else can manipulate to these, but there will be, I guarantee you, a question on the AP test that just literally says, find the limit of sine of 6x over 2x. Find that limit. And you look at that, if you do not know this particular rule, you won't really know how to do it. It's going to be impossible, right? You plug it in, it's going to be 0 over 0, right? The sine of 0 is 0. Plug it in, it's going to be 0. And you won't know, like, how do you manipulate this sine, right? Right, sine of 0, remember our unit circle, sine is the y direction, 0 degrees is horizontal, that's on the 0 spot. So you have 0 for the top and 0 for the bottom. So it's not going to work. You could graph this, sine x over x. You could graph it on a calculator, and you'll see that it goes to 0. Or these ones go to the fraction 2/5. But all you need to do is, if you memorize these rules, that'll be all you'll need. 1 minus cosine x over x, not cosine minus 1. That's different. 1 minus cosine. I guess cosine minus 1 is just a negative version of it. Well, anyway. These are our rules for trig limits. Memorize these, and that'll be it. Okay? So squeeze theorem and trig limits. Let me tell you what I want you to do with these. Let me stop sharing. Any questions? Can I stop sharing now? I'm going to stop the recording.